Very nice. So this is my pleasure to introduce Kristan Jensen, who is visiting us from University of Victoria in connection with his application to FTPI senior position. So Kristan got his PhD in 2010 from the University of Washington in Seattle. And after that, he went on to a postdoctoral career at University of Victoria and Stony Brook, subsequently being employed by San Francisco State University, and currently he's an associate professor position at the University of Victoria. Kristan has done a lot of interesting work in ADS-CFT correspondence topics. He has been working on various aspects of quantum gravity, both in lower dimensional theories and 4D. He has works that directly relate to convex matter theory and chaos. So we are very excited to hear his talk on black holes.
All right. Well, thank you very much for the opportunity to be here. I put the seminar here in quotes. I'm going to try to make it so that first half of the talk is very accessible, kind of colloquium level, and then we'll have to dive into some technical details. Please do not hesitate to ask questions along the way. So plan for today's talk is as follows. So I want to kind of review some long-standing thoughts about in the community about how we should really think about black holes and quantum gravity as quantum mechanical systems, in particular as chaotic systems. It's been a viewpoint that's been emerging particularly lately. We'll then bring holographic duality to bear, which will give us some fresh perspective on the quantum mechanics of black holes, where we can understand, like, are they really adhering to the postulates of quantum mechanics and so on in a controlled way. From there, we'll talk about connections with wormholes and the level statistics of black hole microstates. And then in the last part is the second half of the talk, we'll, assuming our time comes out correctly, and that's where I'll discuss some new results that, I guess I should have said this at the outset, were obtained largely in a series of papers that are here on the screen. I'll flash it later. Collaboratively with Jordan Cutler, who was a student that I supervised and is now junior faculty at Harvard. All right, so
can you hear me for a second? Just a second.
Oh, yes.
Can you stay closer to microphone? Sometimes you hear well, sometimes not.
And also show the screen to everybody.
This is probably difficult. The screen is not seen. We can see slides on our screen, but when we see you, we don't see screen.
Yeah, and you can see slides at least. Can you?
Yes, we can see slides. Yes.
Okay, so if I stand right here, you can see me at least?
We can see you. Yes.
But I cannot see the screen at all.
If you can probably turn your laptop a little bit, we'll see the screen.
Well, the screen.
Alternatively, you can share the screen with us, then we will not see you, but we'll see the screen
I
at
thought
least.
oh, Misha, you cannot see. Okay, this is apology for the technical problems. I thought I was sharing the screen.
No, but we can see
No.
slides. We can
You
definitely
are.
see slides. Yes.
We can like try resharing them. So
Okay.
stop sharing and then sharing it again.
Okay.
Then it might work. 'Cause it's
Okay. So let's try this one more time.
yeah.
Can you check that the audio input is from the microphone? Shouldn't the better position?
Yeah. So you
Well, I think the problem is that the microphone that Misha and Alexei are seeing is through the computer.
Yeah.
But then the
Yes.
one that
Let's,
you guys are.
yeah. We can like
Oh, I see the screen.
great.
Oh,
So
fantastic.
It was yeah.
Okay.
Let's also check the audio input in case there are like a few microphones.
Black holes and chaotic quantum
yeah.
system. Enter ADS CFT. Right? That's what's written.
Yeah, but we could see this even before. It's his slides.
Huh?
We could see this even before. These are his slides.
I think Misha could not see it before for some reason, but he sees it now, which is the important thing.
Okay.
Yeah.
Okay.
Okay, and maybe we'll go back to title slide for Misha's sake. So title, that's me. And then there's some papers at the bottom that this talk is based on that we will build up to. Okay. Right. So let's get into it. So where do we begin? Let's briefly recall how classical gravity works before discussing effects in quantum gravity. So thanks to Einstein at the beginning of 20th century, we learned that we perceive as the gravitational force is in fact the shape of space-time itself. That space and time are unified together through something combined, something that we call a metric that measures distances locally in space between a point at some location and one a small displacement away. Metric tensor encodes the small distance between those 2 points. From metric, one can define curvature, and curvature plays the starring role in our understanding of classical gravity or general relativity. And well, thankfully, Hilbert gave us more than equations of motion. He told us how we could formulate general relativity from an action principle, where the metric tensor G mu nu plays the role of the fundamental field of the theory, of the classical theory. Now, shortly after, beginning with Schwarzschild, it was realized that there are non-trivial solutions in general relativity that describe black holes, something that has been now experimentally confirmed thanks to astrophysicists more recently. And there's a long and interesting history of black holes within the context of general relativity. From the point of view of solutions of the classical theory, they're extremely simple and labeled by only a handful of data points: their mass, their charge, their angular momentum, and in higher dimensions, well, more things. Of course, in nature, one does not find stationary black holes. One finds black holes that are formed from dynamical processes, from the collapse of dying stars. And when you prepare a talk like this, you also find interesting bits of historical information. So as far as I know, the first supernova that presumably gave birth to a black hole that's ever been discovered by humans was recorded in 185 AD in China. Here, this is a picture of the outgoing gases from the hulk of it. Okay, so black holes in nature are this, but from the point of view of theoretical physics, we can idealize black holes as being stationary configurations within general relativity. And if we adopt that point of view and fast forward in time a little bit to the 1970s, there were a series of seminal papers, mostly due to Bekenstein, Carter, Bardeen, and Hawking, where they worked out a bunch of relations that stationary black holes obey. So and I've written them here on the left. probably this audience has seen these things before, so maybe I won't dwell on them too much. I will say that, so here, what are the various quantities involved? Kappa is the surface gravity that you would feel if you were standing on the event horizon of a black hole, the surface by which once you go in, you can't come out. M is the mass of a black hole. A is the area of its event horizon. J is its angular momentum, and Q is its charge. First statement says that those four quantities are not independent, they're related to each other. Second equation says that area increases as time goes on. And third, that the area is positive. And well, if you stare at these things for more than a moment, they seem familiar, especially if you've taught a class in thermodynamics. These resemble the 0th, 1st, 2nd, and 3rd laws of just ordinary thermodynamics, with kappa playing the role of temperature and the role of the area being played by entropy. This series of revelations gave birth to, well, something that's now just called black hole thermodynamics, which is the observation that black holes behave, black holes in just classical general relativity, as though they are thermodynamic objects with an entropy, area divided by 4g Newton, and I've suppressed all the other fundamental units like h bar and c. Now, this entropy is enormous. So, you know, the Newton's constant is roughly the Planck length squared in 4 dimensions. And so if you compute this entropy for, say, a solar mass black hole, you get an incredible number. So the sun, if you just estimate its entropy, you get something like 10 to the 35 in SI units. And if you were to imagine taking the sun as it is and just, you know, some malevolent power in the universe decides to compress it into a black hole, we no longer have life on Earth much longer after that, we all die from the cold, then the entropy would go up by a factor of 10 to the 19. So, okay, so black holes behave as though they have entropy in enormous amounts more than any other objects known in fundamental physics. Now, this idea, you stare at it for a while, it was, it's been kind of codified more recently, but it gave birth to an ideology of sorts at the time that maybe we should think of black holes, at least viewed from the outside, as honest-to-God quantum systems, and where this entropy is not just some object in thermodynamics, it's really counting something in the sense of statistical physics. There's an underlying spectrum of states. Black holes would be described by some Hilbert space with some microstate spectrum that, when counted, gives rise to an entropy that's at least in the semi-classical regime, area by 4g Newton. And this has been, you know, this was an idea I think that was historically pushed more by Bekenstein, and now it's colloquially known within formal high energy physics as a central dogma of black holes, sort of a guiding principle. And I stress that at least at this point in the talk, this is just a claim. Now, if we take this a little bit more seriously, what would we get? Well, what we would get is that when we look at a black hole from the outside, we're dealing with a system that has an enormously complicated microstate spectrum. You would infer a mean density spacing between energy levels from the entropy of order e to the minus entropy, that is e to the minus area by 4g Newton. That's an incredibly finely spaced Dirac cone, non-perturbatively small level spacings. So your picture that you would have then is that there's some very, very finely grained cone of microstates that then if you coarse grain over any appreciable energy scale will give you a very large smooth density of states from which one could extract a coarse grained entropy that would be presumably what we see in classical general relativity. Now, a natural question one could ask at this point is, can you learn more if black holes are really quantum systems? And perhaps the most natural next question to ask is that of level statistics. So there's a major insight in 20th century physics that really goes back all the way to Wigner and Dyson and then many others afterward, that if I have a generic chaotic system, not an integrable one, not one like a harmonic oscillator where all the energy levels are determined essentially by symmetry, then, well, the spectrum of energy levels will exhibit some repulsion. And the statistics of the energy differences is an interesting quantity that exhibits universal features for a wide variety of quantum systems. So for instance, if we talk about the what's called sometimes short-range repulsion, or the differences between adjacent energy levels, and you build up the statistical distribution of those nearest level spacings, well, you, how to say, one finds that there's an average level spacing, and that if one looks at the number of levels that have very, very small spacing, much less than that, it decreases linearly. And this is a result that one can observe for going back to Wigner in the spectra of atoms, nuclear spectra, but one can also find it in many body systems and just an enormous variety of contexts. And in fact, the curve that one gets, say in the context of nuclear spectra, is very closely fitted by the prediction of something called random matrix theory, where you would model your Hamiltonian, whose energy levels you're studying, as being drawn from a statistical distribution, an ensemble of random matrices, of random Hamiltonians, in the limit where the rank of that Hamiltonian is very, very large. I've on this plot here, the curve that kind of sweeps down like this is the Poisson distribution, and that's what you would expect for the distribution of energy levels in an integrable system. And of course, this is quite different from what one sees for generic quantum systems. Now, that's the short-range repulsion. There's a remarkable result that builds on top of it, which is that short-range repulsion builds up to long-range repulsion. It's a bit floppier, but it still is there. And here I've indicated what it is in the context of if you have time reversal symmetry, and where the energy level differences are much larger than the average level spacing, which will be e to the minus s. In that case, with basically any kind of coarse graining imaginable, whether it be an honest-to-God averaging over Hamiltonians, as what finds in random matrix theory, or just some kind of joint coarse graining, one finds a two-point function, correlations of the fluctuations of the density of states that behaves like minus something divided by the difference in energies squared. So you get an anti-correlation. So this is a repulsion, and it gets stronger and stronger the closer those energy levels get to each other. This result has a nice connection to FTPI, is bolded here. So this was something that was studied by many people over the years, including by Altshuler and Boris here. And this role is going to play a starring, this result is going to play a starring role in the rest of this. So this is something that is universal for a wide variety of quantum mechanical systems with time reversal symmetry, and where the spectrum is, microscopic spectrum is chaotic. And no, you can generalize it to.
I know that time reversal is broken, but it's broken a little bit, right? So
Yeah. No, I'm focusing on a time reversal case here because I want to give one example of these formulas that will connect readily to results that I will establish in quantum gravity later. But there's other versions of this where, say, time reversal is absent, or you have some other, or maybe it has an interplay with fermion number or what have you. Okay, so I flashed here again, what is that result from previous slide? A helpful thing to bear in mind is a sort of canonical ensemble version of that result. So what you would see if instead of looking directly at fluctuations in the density of states, you looked at fluctuations in trace e to the minus beta h. That is to say, let me double Laplace transform this. And what you get is some very simple expression, 1 over pi, and then ratio of square root beta 1, beta 2 to beta 1 plus beta 2, where beta 1, beta 2 are the effective inverse temperatures that you would get from Laplace transforming E1 and E2, the two energies. Hold that result. So maybe I'll even write it since I have actually there's no pens here on the board, are there? Do we have a pen that I can write it so we can keep it? Because it's going to show up as the talk goes on. Excellent. Thank you very much. So raise e to the minus beta 1 h, raise e to the minus beta 2 h, subtracting all fluctuations, approximately 1 by pi, beta 1, beta 2 over beta 1 plus beta 2. Energy is anywhere in the bulk of the spectrum, provided that the density of sorry, yes, here, good, thank you. So picture in mind here, from random matrix point of view, is one where the mean density of states begins at 0, and then we're looking away from 0. If we included some sort of threshold energy, then this would just get shifted by an e to the minus beta 1 plus beta 2 times the threshold E naught.
State goes like a semicircle.
Not semicircle, it just has to be very large.
Here is the square root. But the formula shows.
Yeah, this formula hasn't, yeah, that's right. There's square root edge, but it doesn't have to be semicircle in the bulk of the spectrum. Yeah. That's right. Okay. Another thing to keep in mind, there's another way that people sometimes think about this, which is a real-time quantity. Instead of considering fluctuations in, say, the partition sum, consider a time evolution operator, e to the minus IHT, correlated with e to the plus IHT, and then a little bit of e to the minus beta h to regulate physics in the ultraviolet, say. For instance, if we have a system where the spectrum is unbounded above, as one finds in continuum quantum field theory. Well, in that case, this is called spectral form factor, or it's an example of a spectral form factor. And then the regime that corresponds to long-range level repulsion is one where, well, we can basically stick beta 1, beta 2 as beta plus and minus IT in here, and you see that this becomes something that's linear in time t at very late times. This is something called ramp. In spectral form factor, it's a very robust result in quantum many-body systems. And on this plot here, this is spectral form factor for a particular system, SYK model. This is the regime that I'm discussing, where this time scale, this is e to the s. Some other transition happens. It's described by the physics after that, at a plateau. This is essentially the physics of short-range level repulsion. There's this very large domain here where one gets this ramp. And that's something that we can focus on. We can ask, this is a robust feature of quantum many-body systems. Can we see it in gravity? Is it a property of black holes? That's the question that should be in the back of our mind throughout this talk. Yeah, so again, to recap at this point, we have this central dogma, is it actually true? That's a question we can tabulate. Another question, what else can gravity tell us? Can it give us the level statistics? And another question is, do we really, how much can effective field theory tell us? Do we have to know the full details of non-perturbative string theory in order to answer these questions, or can we proceed with an effective field theory treatment of general relativity? Okay, so now ADS-CFT is going to enter the game. In case you haven't heard, about 30 years ago, there was a remarkable discovery made by Juan Maldacena that has, well, it's now called ADS-CFT. So at the time, the result was, so I don't have the time to go into all the details of where all this came from, but that was a quantum field theory, and it maximally supersymmetric Yang-Mills in 3+1 dimensions. It's the quantum field theory that lives on a stack of coincident T3 branes within string theory, that this ordinary, well, relatively ordinary quantum field theory was completely equivalent to a system with a quantum gravitational theory, namely type 2B string theory,
on ADS 5 times S5, where ADS is anti-de Sitter space, space-time with constant negative curvature. You may be able to do the simple computation that 5 plus 5 is 10, which is the number of dimensions that string theory lives in, so at least that checks out. ADS is anti-de Sitter. That's half of this acronym. The other half is CFT, short for conformal field theory. N equals 4 is not just any old quantum field theory, it's what's called a conformal field theory. It enjoys the maximal amount of symmetry that any quantum field theory can have. And the equivalence between these two things, ADS, CFT, is, well, what we're talking about right now. Now, at this point, ADS CFT is an extremely well-tested, but strict, from a point of view of mathematical physics, unproven conjecture. However, there's so many tests that every single time people come up with a new precision test to throw at it, it passes with flying colors. So for practical purposes, it's something that's taken as an article of faith in the community. And if you really took it from that point of view, you can even think of defining non-perturbatively what we mean by string theory, at least in ADS, through the dual CFT. In that case, through N equals 4 super Yang-Mills. One of the earliest results in ADS CFT concerned black hole physics. So that result was that if I take conformal field theory at high temperature, the gravity dual of that is an ADS black hole. And how does this work? Well, quantitatively, the partition function of your CFT at inverse temperature beta would be the black hole partition function at the same inverse temperature. And under the duality, then, CFT thermodynamics becomes black hole thermodynamics. And moreover, CFT microstate spectrum becomes, you would understand it as the black hole microstate spectrum. So already at this first stage, we've got some mileage. We have seen that at least within consistent theories of quantum gravity and ADS, like string theory, that ADS black holes adhere to the central dogma. They really behave like quantum mechanics.
Excuse me, can I ask a question? When you introduce, can I ask a question? I'm sorry. When you introduce temperature, you lose supersymmetry. So simultaneously in super Yang-Mills, you lose super, and it's no longer conformal. So how can you comment on that?
No, absolutely. So well, what is there to be said? So the statement is that when we talk about N equals 4 on Minkowski space at 0 temperature, we're talking about a supersymmetric theory.
Yes.
And okay, it can be mapped to some other supersymmetric theory, type 2b, string theory, blah, 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 blah. But now we can, of course, deform both sides of that. If those two things are really equivalent, we can deform both sides.
Okay.
That's the sense in which, so this duality persists under deformation, including under a finite temperature deformation.
And this the theory on the field theoretic side is still conformal, because temperature is dimensionful parameter. So usually dimensionful parameters ruin conformal nature, right?
That's right. Effectively, you're studying something that enjoys conformal symmetry, but in a conformal symmetry breaking state.
Okay. Thank you.
Yeah, thank you. Okay, so let's take this a little bit further from the black hole thermodynamics in ADS, and also from the knowledge of other states in ADS, we can reconstruct what the density of state is, at least approximately, for holographic conformal field theories, or equivalently for black holes too. And the picture.
Should I think of is this like internal excitations of a black hole, or these are the states that I will discover if I drop a particle one by one into the black hole?
So the question for the Zoom audience that Maxime is asking is, what physically are these black hole microstates? And answer is that no one really knows. What all I've said in this slide is that the spectrum of microstates is equivalent through duality to the spectrum of microstates in an equivalent quantum mechanical theory, and that say in n equals. Now, this is not a very satisfying answer from the point of view of, well, what is it? Can you hold it in your hand? Is it some, you know, rearrangement of space-time and so on? But the problem is that any kind of, you know, hold in your hand explanation for what the microstates is, like, how do I compute with this? How do you know? How do you falsify if that idea is right? Best thing that we have at this stage is using a dual description to tell, okay, these are microstates in a dual description, and that's the best we got. Okay. Speaking of which, so we would infer from black hole thermodynamics an enormous density of states above some threshold energy with something that's growing non-perturbatively with the Newton's constant. And then, at least in ADS typical realizations of ADS CFT, there's also states and energies much, much less than the threshold to make the lightest black hole. So for instance, I can take ADS and I can put a string into it, or a brain, or some other such thing. So it's the light states, and then there's an enormous density of black hole microstates. Yes.
So you said using black hole thermodynamics.
Right.
How do you track it?
Sure. I mean, I just have in mind inverse Laplace transform from nothing special.
So you really only know is the black hole.
That's right. That's right. And sometimes, yeah, that's right. That's enough to reconstruct the picture that is on this slide. I would be remiss if I didn't mention that because we're typically talking about supersymmetric CFTs and theories of supersymmetric gravity, that sometimes there are additional states, a whole lot of them sometimes, that are dual to supersymmetric black holes at threshold. And well, that has proven to be a very useful thing to study in this world, whereby, well, let me put it this way. So one could ask the question in ADS CFT, okay, we see black hole thermodynamics and so on. Can we predict from first principles what we should measure for density of states in this regime? That's a very hard question to ask in holographic CFTs. Something that is actionable is to count the degeneracy, however, of supersymmetric states here appearing at threshold. And that is something that has been done in a variety of contexts. And then you can ask the question, does the counting of those microstates match the entropy of corresponding supersymmetric black hole horizon? Yes. Yes, that's right. Yeah, these are BPS states. There's a few places where one can do this. And I have in mind here within all the context of ADS CFT. So at least in the context of ADS3 realizations of holographic duality, where the dual description would be two-dimensional, then one can do even better than looking at the super BPS microstates at threshold. One can go all the way into the bulk of the spectrum. There are a bunch of lovely matches there, first of which dates back at least to work of Strominger and Waffa and goes on to this day. There's other more recent work looking at the degeneracy of certain supersymmetric black holes in ADS4 by Francesco Benini and friends, and also, again, Francesco Benini and friends, Ofer Aharoni and others in ADS5. Yes, Tony.
Gravity here is ADS.
Yes.
So can you actually connect it to zeta?
That's something that people would love to do, and at the moment there are, I would say, there are some attempts, but it hasn't settled into something that's truly reliable. That is a hope. That is a hope. Yes. Yeah. A supersymmetric black hole, these are, from the gravity point of view, these are spacetimes that emit killing spinners. So they preserve some fraction of supersymmetry. And then microscopically, they would be composed, the expectation is that they would be composed of microstates that are annihilated by the corresponding supercharges, therefore BPS. Yeah. Okay, so let's keep going. So we've talked about how ADS CFT is validating the central dogma. Now I want to talk about level statistics. And to do that, we have to go beyond classical gravity. So we need to start discussing a little bit of quantum gravity and what I mean by this. I'll be doing so in the path integral approach today. And because I'll be studying kind of thermal physics, I also need imaginary time formalism. So let's discuss each of these briefly in turn. So we'll go back to the basics here. Let's remember how double slit interference works. When the usual undergraduate treatment, you have a light source, produces waves, pass through two slits, you add them together, you superimpose them, and you get standard interference pattern on the other side. There's another way of doing this where you sum over paths, where I look at all possible trajectories that connect my light source to a point on a screen where I want to know, well, how much light gets there. And well, thanks to Feynman, we know that we can sum over all possible such paths, weight them appropriately by the action that a particle would take traveling from the light source to the screen, construct the phase, e to the I action divided by h bar, sum them all up, and that gives me the total amplitude to get that I would see on the screen. And this approach to quantum mechanics is called path integral approach. And this is the one that generalizes most readily to everything that we do in quantum field theory and quantum gravity, where, okay, central formula is that your amplitude is a sum over, well, if I'm talking about quantum field theory or gravity, a sum over what are called field configurations, the analog of paths. And I weight them by a factor of e to the is over h bar, and henceforth I'll take h bar to 1, work in a convenient choice of units. This is, the standard model of particle physics is phrased in this language. And we can do the same thing, at least naively, in quantum gravity, where the basic field content, that the thing that we would sum over, are configurations of the metric of space-time, and then whatever additional degrees of freedom, electrons or photons or what have you, where I would call that matter more generally. That's half the story to form a path integral. The other half is what the action is that you would start with. And in this context, what I have in mind is just Einstein-Hilbert with a cosmological constant and then some contribution from matter. Now, this formula, as written, is a nice and naive starting point, but of course, it's a bit of a lie, famously, because at least, for instance, in four-dimensional gravity, Einstein gravity is not normalizable. It's not renormalizable. So, one way, roughly speaking, you can think of this integral as not convergent. So for practical purposes, if we're interested in scattering amplitudes, this is fine as long as we study small momentum transfers, or if we're considering processes where spacetime is not very strongly curved. Otherwise, we have to work in the ultraviolet completion, something that for which this does make sense. And the only real examples we know of where we know how to do that are string theories or gravity in less than 4 dimensions, where the gravitational interaction is actually renormalizable.
People would say that Lipschitz gravity.
Some people would say that, that's right. Some people, sorry for the Zoom, some people would say that Lipschitz gravity is a perspective completion as well. I'm not going to comment on that. Okay, that's so much for the gravitational path integral, what I mean by quantum gravity for this talk. Let me also remind you a bit about imaginary time formalism. Since we're talking about thermal physics, trace e to the minus beta h. How do we talk about this from a point of view of path integral? Well, the way to think about it is that e to the minus beta h is the evolution operator in imaginary time. In the same way that the ordinary evolution operator minus IHT is invisible on the real part of the time, we can think of delta t as being minus I beta And then the evolution operator becomes the Gibbs weight. And if we're interested in the problem of computing a thermal trace e to the minus beta h, where we have this evolution operator in imaginary time, and we consider the trace, that amounts to periodically identifying imaginary time by an amount minus I beta. Or if I call imaginary time y, amounts to identifying y modulo beta. This is sometimes called Euclidean formalism, because if we're talking about a relativistic theory at finite temperature, then, well, if we're studying a relativistic spacetime, say for a conformal field theory on a sphere, then my Lorentzian signature metric, the theory would be on its minus dt squared plus the sphere metric, and that becomes something that is totally Euclidean under continuation. And the upshot of all this is that if I'm interested in partition sum, well, that's a Euclidean path integral. It's a path integral over configurations on a Euclidean spacetime with an S1 whose size is the inverse temperature, and then whatever space is. Let's take this and go back to ADS-CFT. Under the ADS-CFT dictionary, this would tell me then that my thermal partition function, the trace e to the minus beta h, this is something that I could draw like this. This is what I have in mind here is a sum on the right-hand side over higher dimensional spacetimes that asymptote to a boundary that is exactly that I'm discussing here for thermal QFT. It's thermal circle times a spatial sphere in this case. And if I were strong enough to perform the sum over that spacetimes, that would reconstruct for me the thermal partition function of my dual CFT. Now, we don't know how to do that sum exactly, but, well, fortunately, there is a saddle point approximation to that sum. There's a classical approximation that we do know. And if we're at some temperatures above some critical amount, that saddle point is nothing more than the Euclidean black hole. This is where that result that I advertised earlier about how CFT above some kind of critical temperature, how it's an ADS black hole, that's where that comes from. And the geometry in question, it's something that's sometimes called a Euclidean cigar. It's just the analytic continuation of an ordinary black hole. So here, if y was IT, this would have a minus sign in front of it. This would become a Schwarzschild ADS metric. But in this case, in Euclidean signature, this geometry caps off at some value of r in a smooth way. Yes. Good. So I have in mind conformal field theory on a sphere, and that's set fixed as a scale. So I'm working in units where the radius, I can pick that radius to whatever I want. I fix it to be 1. Or in other words, I work in the dimensionless quantity is, or rather TC is some number divided by r, where r is the radius of the sphere. Yes. So having a radius for a sphere also break, well, how to say, if I was at 0 temperature, actually having the radius for the sphere does not break conformal invariance. Then one way to think about this is if you know anything about, do you know about operator state correspondence in CFT? Okay, roughly speaking, if I take the plane, I can do stereographic projection, which preserves conformal invariance, and it maps the plane to the Einstein, to the basically the radial direction, which now plays the role of a time, times a spatial sphere. And what I'm doing now is I'm considering that at finite temperature, where I periodically identify the time direction. Okay. So that's the dual to partition function. Your next best guess then, if we want to talk about level statistics, so the product of the partition function with itself, is I would sum over spacetimes with 2 boundaries, not just 1. Where one boundary, if S1 at a radius at a size beta 1 times the spatial sphere, And the other one is the same thing, but with beta 1 to beta 2. And you might think too that correlations in the spectral density would come from connected geometries, things that correlate the two. But if you think that and you start taking that line of logic seriously, you run into a couple of immediate problems, one of which is conceptual and one is practical. The conceptual problem is as follows. So in proper ADS-CFT, the partition sum is a number. It's a very complicated number, but it's still a number. As a result, when I consider, say, the product partition function at beta 1, partition function at beta 2, that's just a number, and in particular, it factorizes. So what you would get then is that product should be Z beta 1, Z beta 2. We already said that Z beta 1 is the sum over things that asymptote to boundary at beta 1. Z beta 2 is something that asymptotes to boundary beta 2. What else can there be? Well, in a theory of quantum gravity, you would expect to sum over all possible spacetimes that connect these two boundaries together. In a similar way as in particle physics, when you consider a scattering amplitude, once you fix the in and out states, anything that can happen does with some weight. Wormholes, connected geometries that would connect these two things together, would be such a hypothetical contribution. And in a string theoretic context where geometry is not sacrosanct, there might be other more complicated non-geometric contributions to this problem that we do not understand. Let's focus on the wormholes for a moment. So they seem to encode things that correlate the two boundaries that would give you more than the product Z beta 1, Z beta 2. And it's very confusing from the point of view of microscopic ADS-CFT. It would give you a non-factorizing contribution to this, and it would behave for practical purposes if it's there, like it would signal the existence of an ensemble average. That what I mean by Z is not actually Z, but it's that H is drawn from a distribution, and Z is the average partition function obtained from that distribution. And ZZ would be the 2-point average. Is that actually true? And again, in honest ADS-CFT, we expect it to not be the case, but well, now we have to really to confront this question. That's the conceptual problem that this raises. There's also a practical problem, which is that there are no solutions to Einstein's equations that connect two boundaries together like what I'm drawing here. In fact, there's a theorem due to Witten and Yau that this is the case. And this is the Euclidean version of the standard statement that we know in ordinary general relativity, that there's no traversable wormholes between asymptotic regions. There's shielding. And the practical import of this is that if these wormhole amplitudes do exist, if they're a real thing in gravity, then they have no semi-classical approximation. So now here I can talk about some progress on these fronts. I'm timing myself for an hour. Okay. So let me summarize what are the major results that we have established over the last few years in this vein. So the first one of which is a leading contribution, an honest-to-God wormhole amplitude, in a very simplified setting in quantum gravity, namely in pure three-dimensional gravity with negative cosmological constant. This is not string theory. This is a scenario where the gravitational interaction is normalizable, where we can make sense of the sum over metrics, but it's not, full-fledged ADS string theory. And therefore, we don't have good reason to think that there should be factorization, and we should be dealing with a single theory. And then this wormhole amplitude that we compute indicates, it's very consistent with, the existence of an ensemble average in a putative dual description. The result that we find, I have this thing here, it generalizes this answer once we process it. And there it gives a generalization of Alt-Schumer-Shklovsky in the context of two-dimensional conformal field theory. Low-dimensional gravity is great, but of course we want to know about the full thing, about proper ADS-CFT, proper string theory. So I'll give another result where we talk about long-range level repulsion in honest-to-God ADS-CFT. and where we don't have to make bad assumptions like that when we talk about n equals 4, we're talking about an ensemble average thereof. The last thing I'll get to, if I have the time, is some work on what's called parametric correlations. Okay, so where to begin? So let's begin with this first result, this same wormhole amplitude in pure three-dimensional gravity. So these wormhole amplitudes, I mentioned, they have no semi-classical approximation. There's no saddle point to the Einstein's equations that with these right boundary conditions. And because of that, if they mean anything at all, they really mean a complete sum over metrics plus maybe even other stuff. And because there are then spacetimes that connect two boundaries with arbitrarily small bottleneck, arbitrarily large curvature, these wormhole amplitudes are very sensitive to the ultraviolet. Now, in a stringy context, that means they're sensitive to the behavior of non-perturbative string theory. And well, as far as that's concerned, we're up a creek because we don't yet have the technology to compute such things in proper string theory. There's a nice little exception that Lorenz Eberhard worked out a few years ago in the context of the NSNS vacuum of ADS3 times S3 times M4 with a single unit of NS flux. But in general, we have no hope at the present time. So the option route that we took, and then I'm just going to describe in the next few slides, is to work in less than 4 space-time dimensions where gravity is power counting renormalizable. And I'm going to focus on the example of three-dimensional gravity. And here our large dimensionless parameter, or equivalently small dimension, can flip it and small, is going to be the radius that I infer from the cosmological constant divided by g Newton. If I'm talking about semi-classical 3D gravity, that's a very, very large parameter, and that'll control quantum effects. Now, to proceed, we have to talk, okay, the thermal partition function in ADS3. What is that thing? Well, we said that's going to be that there's a thermal circle, a time circle, and then there's space. My dual CFT is living on a 2-dimensional torus. How do I parameterize such tori? The standard thing to do is to work with a complex position, and then the torus is labeled by its complex structure type, which encodes sort of the imaginary part is the inverse temperature, and how much it's tilted refers to the chemical potential for angular momentum. And this thing in CFT can be decomposed nicely in terms of a contribution from the vacuum state on the circle, plus all those states related to it by conformal symmetry. Those are the descendants of the vacuum, plus a contribution from, well, everything else, primary states, and, well, their descendants as well. So in the same way that in ordinary quantum mechanical systems with rotational symmetry, if you have a spin J multiplet, that means there's 2J plus 1 states that are all degenerate with each other. In the land of 2-dimensional CFT, if I have a primary state, there are infinitely many others whose energy levels and quantum numbers are completely determined by those of the primary. And in this context, it's going to be helpful to mod out by symmetry. Consider just the content of the spectrum or the partition sum that is telling me how many kind of basic states I have, and then there's more that are generated by conformal symmetry. And what I'll define as ZPS, this is counting states that, well, they're primaries of spin S, and I've removed all the contributions from descendants. And why does time reversal matter here? Microscopic CPT symmetry of an underlying CFT will become a time reversal-like symmetry for the Hamiltonian on the sector of primary states of fixed spin. Now, if we're interested in two-point function of partition sum, we're dealing with geometries that fill in 2 tori, the simplest connected one of which is something that looks like this. This direction I can take to be an interval, and then there's a torus. And what we did was we exactly computed this amplitude in 3D gravity. To date, it is the only existence of an off-shell wormhole amplitude in any model of quantum gravity in more than 2 dimensions. Well, it's a very non-trivial thing. And I could...
To the results for gravity. there any way to compactify this down?
Can we talk about that afterward? There is a way, but it involves some subtleties that are, and it may be kind of a misleading relation, actually, if you know something about that. So I'm strapped for time at the moment. So what I can say for how this works in detail, I can't say very much, just given the time constraints, but the basic idea is to completely enumerate the space of gravitational configurations and integrate over them all. That is to say, to compute the full path integral. And the only reason why we have a prayer of being able to do that in this context is that some of the gravitational fields act as Lagrange multipliers enforcing constraints. We can completely solve the constraints, define the constrained space of integration, and that reduced space is simple enough that we can perform the path integral over those configurations. The final result that one gets, there are certain zero modes that are compact, that have a field range that can be computed. It's rendered finite thanks to diffeomorphism invariance. There are things that behave like moduli, except with an effective potential that I'm calling here H and H bar. In fact, the potential is never extremized. One way of thinking about that, that's why the resulting integral that we find does not have a saddle point approximation. And then the thing that one is integrating is a product of Virasoro characters. Now, what I just wrote is actually not the full answer. It has to be dressed up with something that gravity automatically implements such that the full answer respects what's called modular invariance. And whenever I talk about a CFT on a torus, I've parameterized it this way, but there's many possible ways of parameterizing the same torus. I can think of this as a unit vector. This is another unit vector. Any basis of unit vectors will do to parameterize the same torus. Invariance of partition sum under that is called modular invariance. And gravity naturally accomplishes that. It basically dresses up the thing I presented before with a sum over modular transformations. And final answer that one gets for the wormhole amplitude is, well, I can write it in a line, but it's a little complicated. What does it mean? Should have something to do with level repulsion. Well, remember a couple slides ago, I said something about that the natural object to study is the sum over primaries at fixed spin. That's something that reduces all the symmetry in the problem. I've taken care of the fact that I have a translational symmetry and also accounted for all those states whose quantum numbers are fixed by conformal invariance. Well, I can extract that from here essentially by the same thing, strip off descendants, and then Fourier transform to fixed spin. And when I do that, I'll spare you the details of that computation. One gets a very nice simple thing, a two-point function of the primary counting partition sum that is exactly this thing that I was writing before, times a Kronecker delta in spins, plus corrections that go like 1 over beta. So that disappear at very low temperature. And where this E naught, this is the threshold energy of what the black hole in 3 dimensions. These are called BTZ black holes. Been in Canada for a while, so it automatically comes out as Z. And the 1 over betas, okay, these are not present in this expression right here. Those, however, are mandated by the underlying modular invariance of the quantity on the previous slide. Another way of saying this is that quantity on the previous slide gives us the anticipated long-range level repulsion that one would get from a random matrix ansatz for a black hole microstate repulsion, plus those corrections that are mandated by properties of two-dimensional CFT. In terms of spectral form factor, those corrections lead to, if one is familiar with spectral form factor, to power law suppressed fluctuations on top of the ramp. And okay, good. So this result, we didn't ask for random matrix theory. We didn't ask for a ramp, but gravity handed to us anyway. And maybe I should also stress, there's a long-standing question in quantum gravity, whether or not, what is the role of wormholes? Should they compute something? Should we include them? Should we not include them? And these were sort of undecidable questions. How do you know? Well, from this point of view, what we're seeing is that those contributions, if you decide to compute them and see what you get, they encode interesting anticipated known physics, namely long-range level repulsion. Now, a natural question that one can ask, I talked about a ramp. When I showed this plot of spectral form factor before, it caps off at late times. This is called plateau. It's ultimately a consequence of the fact that there is an average nearest neighbor level spacing. It's the context of short range repulsion. A natural question to ask is if you can see that in gravity. At the moment, that is beyond us. It's a wonderful question. People are working on it. Yes.
Can you talk to how important are these sort of connected wormhole integrations relative to say disconnected integrations?
Yes. Yeah. So in the okay, so in the context of ADS3 gravity, the disconnected contribution. So in CFT, we can label it in terms of essential charge C as a natural measure of degrees of freedom. In holography, ADS3 holography, that central charge is very large. This dimensionless quantity that I mentioned previously. And the disconnected contribution, this like 2 copies of the Euclidean cigar, is of order e to the 2c. This is of order e to the c, this is of order e to the c. If you know about Carty formula, you can think about that as being a consequence of the Carty formula. The black hole density of state scales like Carty formula. But this answer is order 1. The wormhole contribution. This is from like a perturbation theory point of view. This is a very small, this is an instanton-like effect. Similar to what happens in random matrix theory, where this is down relative to the mean density of state squared by factors of e to the -2 times the average entropy. Okay, I'm going to have to move very quickly here. Let's see, we're doing so I mentioned this amplitude, it's the only one that's on the market. We're computing another one. The 3-boundary version of what I described previously. This is, in general, these amplitudes are incomputable using gravitational path integral, with the exception of this one. Yeah. So it looks like I will not have time to talk about some of the other results about how we can modify this technology that I described previously. We basically were able to adapt it to discuss wormholes and long-range level repulsion in proper full-fledged ADS CFT. I'll say one line about the big idea how we do that. The big way that we do that, so these wormholes would, I said they don't have a saddle point approximation. They would imply a breaking, a factorization. What we do to make sense of both at once is to fix a constraint that correlates the 2 boundaries. And that's very natural from a random matrix theory perspective, which is we look at the microcanonical version of the problem where we fix the total energy that's shared. If I think of this as a system and this is another subsystem, we fix the total energy. That correlates the 2. I'm studying then a non-factorizing observable. And once I do that, now I can find saddle points of that non-standard problem, do all the wormholes, and you match the long-range level repulsion I advert that one gets there. With that, okay, there's a lot of stuff we didn't get to. Lessons from this. You should take the gravitational path integral seriously. It appears, so in particular, wormholes encode interesting physics. They encode long-range level repulsion and plus more, perhaps, in the black hole microstate spectrum. In ADS string theory, there's going to be more than smooth geometry. There'll be other contributions that will in particular ensure that we maintain factorization. And exactly how that works is an important open problem. With that, thank you very much for your attention.
Now, time for one or two quick questions, because there is people anxious to get to the class. Any questions?
So there's, okay, so there's, yes, right. So good. So not, let's see. So the, well, yeah. Yeah. Right. Okay, so a question that's being asked at the moment, there's been previous important papers connecting wormholes to entanglement. Is there any relation between that work and this? So, well, yes and no. I mean, they're different wormholes. So the relation that Juan and Lenny identified in the context of ER equals EPR has to do with, I can think of the black hole, if it's an eternal black hole, as a highly entangled state between two copies of one and the same CFT. And from that point of view, I can think of the geometry that is geometrizing that very large entanglement as a non-traversable wormhole. That's what the two-sided black hole geometry is. I have an exterior of one, I have two black holes, they each have an exterior, but I can't get from one exterior to the other through a time-like trajectory. That's how that story works. And there's some analog of this in the context of lower dimensional gravity as well. These things would be, these are Euclidean wormholes, but if you continue them to real time, these would be things that are traversable. So it's a totally different can of worms. It's one way of thinking by why these are not a classical gravitational effect. You better not see them, because otherwise you have some problems with killing your own grandparents and such. So.
All right. So I suggest that we close at this point because we're in class. So Kristan is here today, tomorrow, and in principle he will make himself available on Wednesday.
Yes.
And so let's thank our speaker.
Okay. Thank you.
Thank you.
Thank you all.
Need to leave the room, unfortunately, but yeah, I would love to talk more about all of that.
Yes, let's. I look forward to it.
Okay.
Okay. Let's turn this off. Thank you all.
Thank you. See you tomorrow.